Hey everyone and welcome back to PrepFusion. I'm Anish and today we'll start the lecture 8 of rectifiers. So we have studied about full wave, half wave rectifiers, full wave rectifiers with our RLE load, RL loads, then RE loads. So in today's lecture we'll solve questions of full wave rectifiers. Okay, so like these questions will be very interesting and these are all very conceptual questions and these are not gate POQ. So gate POQs also will solve, but these were very conceptual and good questions that I have picked, so that will clear your conceptual doubts. Whatever you had conceptual doubts, that will clear those. Okay, so this is the first question. What I will do, okay, I will first show you all the questions, right? You can take the screenshot and then try to solve for yourself. So this is the first one, this is the second one, this is the third one, fourth one, then this is the fifth one, okay, sixth one, seventh. There are total 9 questions, 8 and 9. So try to solve it by yourself. Don't give yourself like that cheating thing, right? Don't do that, because in gate examination you won't be able to cheat. So try to solve it by yourself and then obviously you can see my solution. So it's better that way, it's better. Okay, so let's start here with question 31. So what is this question telling us? In a single phase full converter, delivering a full converter is delivering a load as shown. So it is delivering a load as shown below. The output voltage waveform is shown below. So output voltage waveform is shown below. Then comment about the continuity of the load current. So what is our VS? VS is basically what? VS is equals to Vm sin omega t. Okay, and the output voltage, right, I can observe from 0 to alpha it is negative, something negative, but Vm sin omega t is something positive, right? And from alpha to pi it is again positive, and then from pi to 2 pi plus alpha it is again negative. So what is actually happening? So if I observe here, like it is telling that from 0 to alpha, right, from 0 to alpha my voltage, output voltage is minus Vm sin omega t. So it is negative of supply voltage. So from 0 to alpha it is negative of supply voltage. So from 0 to alpha my VO is negative of supply voltage. When does it happen? When is my output voltage negative of supply voltage? When my T3 and T4 are on, right? When my T3 and T4 are on, this natural pair is on, then only it is possible that it is exactly equals to negative of supply voltage. Then exactly at alpha, what happens? Alpha, I generally trigger my SCR, right? Trigger my T1 and T2 SCR. So alpha, it is again becoming VU is equals to VS from alpha to pi. Okay, alpha to pi. Oh no, not alpha to pi. Actually, this is positive only, right? This is only positive. So from alpha to pi plus alpha. So this is alpha to pi plus alpha actually. Alpha to pi plus alpha, it is exactly equals to Vs, right? Why? Because after pi, my Vm sin omega t is also negative. So from alpha to pi plus alpha, what I can say, this is simply equals to Vs. And next what is happening? Then again from pi plus alpha, it will go on until 2 pi plus alpha, it will be simply equals to minus Vs. Okay, so what is actually happening? This happens when my T1 and T2 are on. Okay, so this can only happen that generally what happens in the positive half cycle, T3 and T4 are reversed in the reverse blocking mode. This can only happen if T3 and T4 are on. That can only happen when the load is inductive. From this I can conclude load is inductive, else it can never be equals to minus Vs during the positive half cycle, right? It can never be equal, but load is inductive, that's why it is keeping T3 and T4 on. Here, right, what does it? Either it is equals to plus Vs or minus Vs, right? Either it is equals to plus Vs or minus Vs. Our voltage, right, output voltage VO is never some constant value like E. Okay, whenever VO is equals to E or VO is equals to always 0, that means what? The current has gone to 0, but it is never. Hence what can I conclude from this? I can conclude that my load is conducting, load is in continuous conduction mode. Okay, load is in continuous conduction mode. So yeah, in this case, right, load will be continuous conduction. Is it like constant or it is varying, but it is continuous conduction? I cannot say from this only this data, but this much I can say is that load will be in continuous conduction mode. So this will be my answer. So this can come as a MCQ, right? They can ask whether the load is conducting continuously, or it is discontinuous, or it is constant. This can be MSQ as well. So it can be constant as well as continuously conducting, either of them. Okay. So this was the first question. First question was basically clearing your concepts. Next, in a single phase full converter delivering a load as shown below. Okay. Delivering load as shown below. Draw the output voltage waveform and calculate the average output voltage for continuous conduction of load if alpha 1 is this, all this, and alpha 2, alpha 3 are all this. Okay. So like here, right, basically you have been given a single phase converter, and but this time, right, your triggering angles are actually not synchronized. They're different. So for the T1 thyristor, it is 60 degree, and for other thyristors, right, it is simply 0 degree. It is simply 0 degree. So if it is 0 degree, we will understand what do you mean by that. Like 0 degree for this right, this means alpha 3 and alpha 4 are triggered 0 plus 180. Okay, alpha 3 and alpha 4 are triggered for 0 plus 180. So this should be clear actually. So this is 0 degree. Here I will mention it specifically here, 0 degree. This in the positive half cycle, and here 0 degree means in the negative half cycle. Negative half cycle. Okay. So here what is happening is that like they have given us the information. This also will be, this also is same only. Yeah. This is for the, again this is for the what? This is for the negative half cycle. This for the positive half cycle. What information they have given us? The information that they have given us is we have to draw the output voltage waveform and calculate the average output voltage for continuous conduction. So we have to draw it, right? So in the first case, right, my alpha 1 is 60 degrees. So if my alpha 1 is 60 degrees, before that, if I assume that, what will happen? My alpha 1 won't turn on. If alpha 1, like if thyristor T1 doesn't turn on, then will this be on? Will this be on? This will be on, right? Because what happens? I have triggered this as alpha 2 because these two thyristors are in the forward blocking mode in the positive half cycle. So if I trigger this one and I don't trigger this one, this will be on, but this won't be on. And they have told me that like there is continuous conduction of the load. If there is continuous conduction of the load, what will happen is that like this load will try to pass in some current. Now at in the positive half cycle, right, this T4 and T3 get naturally commutated. That is correct. So what will happen? The current needs to flow, right? Because there is continuous conduction they have given us in the question. So let's assume a path. Let's assume that current is flowing through this. Current is flowing through this. Okay, current can flow through this, but this is also on, right? As this is also on, this will basically naturally commutate this, right? Naturally commutate because current can flow through this as well. Current can flow through this as well. So if current flows through this, current can either flow through here or either flow through here. Okay. So what will happen is basically the inductor will try to keep this SCR on. This will be naturally commutated as this one is on, right? Now, if this one is on, I can apply a KVL. What KVL can I apply? So the KVL that I can apply is I can start from here, here, and end here, right? So basically, okay, this is VS actually. VS has been skipped. So in the case A, I'll just take a page. Case A, what is happening? Case A basically, my if I apply KVL here, right? So I have assumed like at omega t equals to 0 degrees, SCR T2 has been triggered. If SCR T2 has been triggered, it will turn on because it was in the forward blocking mode, right? It will turn on. Now as it turns on, what will happen to this T4? So I will find out that, right? So I'll apply KVL. I will start from here, plus VT2, then minus VS, minus VT2. So plus VT2 is 0, right? Because the voltage across the SCR is 0. It has turned on. So 0 minus VS minus VT4 equals to 0. Okay, so what is my VT4? What is my VT4? VT4 equals to minus Vs. VT4 equals to minus Vs, right? And if VT4 is minus Vs and I'm at the positive half cycle, that means VT4 is something negative. VT4 is something negative. Hence T4 will turn off. But current needs to flow, right? Current needs to flow. So it will choose this path. Then it will see two different paths. One this, okay, another this. But this is still not triggered, right? So this is off still. This is still not triggered. This is off. But this was already at on state. This is already at on state. And thyristor voltage, right? Not thyristor. This load voltage in which there is an inductor that will try to keep it voltage as such that this will still keep this T4 on. Okay, not T4, sorry, T3. Okay, this is actually alpha 3 actually, not alpha 4. This is alpha 3, fine. So this will still try to keep it on. Okay, keep it on. Why the inductor will keep it on? Because current needs to flow, right? Current cannot flow through this path because this is off, right? This is off. So current cannot flow through this path. This is off. Hence current has to flow through this because this is all. This has been already turned off. Okay. Anyways, this is not useful because current through this, right, need to flow like this, which is not possible. This here can never allow current in the opposite direction. Okay. So what will happen? Load will keep T3 on. Okay, load will keep T3 on. Hence, as T3 is on, if I want to compute my VO, right? If I want to compute my VO, what will happen? My VO in this case, from 0 to alpha, will be simply 0 volts. If I apply a simple KVL, this is on and this is also on. If this is on, then the voltage, like switch will be turned on and the voltage will be simply 0. So VO will be simply 0. You apply KVL and VO will be simply 0, right? So okay, in this region VO is 0. Now what is happening at pi? At pi, right, both of these are triggered. This T3 is triggered and sorry, at alpha, right? At alpha 1, this T1 is triggered. So as soon as this T1 is triggered, right, this was in the forward blocking mode. As soon as this T1 is triggered, this will turn on. So as this turns on, what will happen is that this T3, right, SCR T3 will be naturally commutated. So due to the potential, you can measure the voltage drop and you will find out T3 voltage to be negative. Okay, so at omega t equals to alpha 1, that is 60 degrees, T1 is triggered. Okay, so we can obviously turn this off because this one will be naturally commutated. T3 will be naturally commutated. So now current can flow like this. Now if you apply the KVL, your VO from alpha 1 to pi will be simply Vs plus Vs, right? Now from pi to pi, right? From pi to 2pi, because these are triggered at exactly close to 0. So these, right, these are acting like diodes. So here what will happen is from pi to 2pi, basically T okay, what I can do is I can reduce the size of this. T1 and T2 will be off. They will be naturally commutated because T4 and T3 will be triggered. T3 and T4 will be triggered. Okay, so from pi to 2pi, what will happen? Basically my T3 and T4 will be triggered and your VO, right, your VO will be basically equals to minus Vs. If you apply the KVL, VO will be minus Vs. They will be on. Okay, so how will your output voltage look like? So your output voltage, right, for this part A will be something like this. So it will be 0 up until alpha 1, that is 60 degrees, or I can name this as alpha 1, or I can name this as pi by 3. Then it will follow the input basically up until pi. Then from pi, right, it will exactly follow the minus of the input, so that is minus Vs. So it will be totally half sinusoid. Then again the same pattern will repeat. You can do the analysis. So it will be same, it will be 0, and it will again go to 0 like this. So it will only repeat. So what will be the average output voltage? So average, VO average, right? If I just compute the VO average, I might need to take this to the next page actually, this one, right? We'll take this to the next page. Yeah. Okay, so what is this basically here, right? What is the can I compute the average voltage? So this, right, this has a time period of 2 pi, not pi. Okay, this has a time period of 2 pi, not pi. So this is just a semiconductor. Actually, I taught you semiconductor without even telling you, but that's fine. We will learn that in the next lecture. But what will be my VO average? VO average, right? This is a periodic waveform which is repeating every 2 pi, not pi, right? Because this is different. This half cycle is different and this half cycle is different. So VO average will be simply equals to from like 1 by 2 pi, pi by 3 to pi, it will be simply Vs. Okay, Vs d omega t, and plus what? Plus from pi to 2 pi, it will be minus of Vs. It will be negative of Vs, right? D omega t. Okay. So my VO of average will be 1 by 2 pi. What is Vs? Vs is Vm sine omega t, that I have just like I think explained here itself. Yeah. Okay, I haven't. So if you haven't, then I should have written what is Vs. Vs is Vm sine omega t. Sorry for that. So Vs is like, if nothing is mentioned, you just assume it as a sinusoidal. So this is Vm sin omega t. So this integration will be what? This will be minus of cos omega t. And first I will do cos of pi by 3 minus cos of pi. Obviously Vm is at the outside. Vm can be at the outside. And this, right, this will be, integration will be plus Vm cos omega t. So cos of 2 pi will be simply 1 cos of 2 pi minus cos of pi. Okay. So here what expression I will get? I will just tell you about the expression. So what is cos pi by 3? Cos pi by 3 is cos 60. Cos 60 is half. Okay, and like this is minus 2 cos pi, right? Minus 2 cos pi. So minus 2 into minus 1 will be plus 2, and cos 2 pi. Cos 2 pi is simply 1, right? What is cos 0? Cos 0 is also 1. So this will be plus 1. Okay, so what will be this equals to? So this will be equals to simply 3, 6, 7 by 2, 7 by 4 pi. 7 into Vm by 4 pi will be basically your answer, right? will basically give answer. It will be almost equals to Vm upon pi cos alpha, where alpha is 0. But here, due to this region, right, where my area was 0, it got reduced. It got reduced by how much? This much amount of value. Okay, so yeah, this will be the answer for part A. And what about part B? So for part B, right, for part B, I am triggering at 45 degrees for the T1 and T2, and triggering at 75 degrees for the T3 and T4. So if there will be same analysis, just a difference will be here. I will just explain in a minute what will be the difference. The difference will be that if I just copy this, so from start the analysis from alpha 1 equals to alpha 2 equals to 45 degrees. So I will start with alpha 1, alpha 2 equals to 45 degrees, right? So before that, I will obviously not start analysis, because that will be difficult. Once we complete it, I will explain actually why I didn't start from there. So if alpha 1 and alpha 2, that is T1 and T2, are triggered at 45, so T1, T2 will be on, right? T1, T2 will be on, and they will naturally commutate the other two SCRs, that is T4 and T3. So they will be on. Okay, they are on. So as soon as they are on, right? Just hold on a second. Was really feeling safely. Okay, so as soon as these two are on, they will naturally commutate these two. As I'm assuming these two are on. These two were on before. Why? Because if these two are not on, right, and these two are off, then everything is off. Then there is no current flow, and that is not possible, because in the question they have mentioned there is continuous current flow. Okay, that won't be possible. So at alpha 1 and alpha 2, these two are on. Okay, and they are flowing the current. So what is my VO now? VO will be equals to simply Vs in the duration of 45 to omega t equals to 180 degrees. Okay, then after 180 degrees, you might say, sir, these two will go to reverse blocking mode, which is correct. These two will go to reverse blocking mode. Whatever you're saying is correct. But as there is continuous conduction, right, and I haven't triggered my T3 and T4, so here there is a load, there is a load. Inside the load, I have an inductor. So that inductor will change its own polarity and will not let this T2 and T3 go to reverse blocking mode, will not naturally commutate this thyristors. Still some current will flow. Okay, it will lose energy. So here, right, what is happening? That inductor was not delivering to the source. It was simply losing energy through a simple wire, right? This this wire, through this wire. But here, in this region, right, from 180 to omega t equals to 180 plus 75, because at 75 I am triggering my SCR. So 180 plus 75 is 255 degrees. Load, power flow is from where? Power flow is like this. So power flow is like this. Load to source. This is the power flow. Load to source. This is the power flow, right? So obviously, in this total duration, in this period, my voltage is what? My voltage is still, VO is still equals to Vs only. So it will be something negative. Okay. So if I draw the first from alpha, right, from alpha 1 here, if I start to draw from here, it will follow the input plus Vs, and it will keep on following the input, right, up until 255 degrees. Keep on following the input up until 255 degrees. Then at 255 degrees, what will happen? So at 255 degrees, right, 255 degrees, this T3 and T4 will be triggered, and they will naturally commutate T2 and T1. So let's copy them. So at omega t equals to what is it? At omega t equals to sorry, 255 degrees, right? 255 degrees. T3 and T4 are triggered. As soon as they are triggered, right, my SCRs T1, T2 will be naturally commutated, right? SCRs T1 and T2 will be naturally commutated. Okay, so this is the case. So as soon as they are naturally commutated, what is my output voltage now? So these will be off and these will turn on. Okay, so here my VO will be equals to what? You can apply the KVL. VO will be minus VS, so it will be positive. So in this, anyways, at 255, right, it was some negative value, but suddenly it became positive, so it will flip it. I will just flip it, right? Okay, I'll just flip it, so it will be something bigger, because this is 45 will be something lesser and 255 will be something bigger. Okay, so yeah, that will be the case. So this, right, this should also be more lower. Yeah, so then what will happen? Then obviously it will just follow the negative of it. So here, right, voltage was going high, then it was going low, so that will exactly what will pan out. Go low, and it will go low until negative. And what negative value it will go until? So here I will stop and then again I will restart. What negative value I will go until? So like this side, they should start at a much previous time. Yeah, here. But this peak should be same, right, for both of them. Peak, like, don't go with my drawing, okay? My drawing is not that great, so don't go with my drawing. My drawing is obviously not that great. I'm sorry for it. So yeah, it will be something like this, not to scale. Okay, so here what is happening is that at this point, right, at what this is basically omega t equals to pi. This is basically omega t equals to 2 pi. Okay, and add this 2 pi. What is happening? Add this 2 pi. After this, right, after 45 degrees, again I'm triggering my SCR T1 and T2, right? T1 and T2. So after 45 degrees, I'm triggering my SCR, and this is up until up until omega t equals to 255 to 360 degrees, 2 pi, right? Next, what is happening is that at 360 degrees, you will say, sir, T4 and T3 will be naturally commutated. They will be turned off. They will be in the reverse blocking mode, and this T2 and T1 will be in the forward blocking mode, and every SCR will be off. That is not possible, because they have said in the question, there is a continuous conduction. So if there is continuous conduction, this inductor will obviously try to keep few SCRs on. This time, right, it will try to keep these SCRs on, because it is not possible for me to turn on this SCR. Why? Because these SCRs need forward voltage triggering. Okay, and I am not triggering it, hence this will not turn on. Okay, this will not turn on. This will keep this SCRs on. If this is SCRs are on, so my VO, output voltage, will still be minus VS. Hence, like, within what range? From 360 to 360 plus 45, because after 45 degrees, again I am triggering my T1 and T2 on, and hence that will naturally commutate my T3 and T4. Okay, so this is 405 degrees. So this will go on until this 2 pi plus pi by 4, right? This will not go on up until this small amount, pi by 4, and again after that VO will be plus VS. So yeah, it will be like this only, and then again it will increase. Okay, so this will be the waveform. This is pi by 4 basically. And what is this? This is 75, right? What is 75 actually? 75 is 75 by 180 into pi. So if I multiply by 15, this is 5, and that is 15 to 10 into 12, 5 by 12, 5 pi by 12. So this value will be 5 pi by 12. Just let me check whether I am correct or not. This is pi by 12 is pi is 180, right? So 180, like if I divide by 12, that would be 15. Yeah, that is correct only, right? That is correct. Yeah. So it is 5 pi by 12. This is pi by 4. So, and this right here, right, before pi by 4, this was just negative only. So this was just negative only coming from here. Okay. So this is the case, basically. This is the waveform. This is my VO waveform. Okay, and like what I can do, I can simply integrate this. So to find VO average. So again, this is a like a cycle of 2 pi, because this, right, this is pi by 4. This distance is pi by 4, and for the from pi to here, right, this is distance is more. So obviously this is not symmetrical about like this is not repeating every pi. This is repeating every 2 pi. So again, my VO average will be, so this type of questions can come where you have to derive the things, right? You can't just mug up the formulas. That's why I recommend you to understand the derivations as well. From pi by 4 to pi, it is not pi, actually pi by 4 to 5 pi by 12, it is actually plus Vs, Vm sine omega t, plus from 5 pi by 12 to this is what? This is 2 pi plus pi by 4. So this will be 9 pi by 4. 5 pi by 12 to 9 pi by 4. This will be minus Vm sine omega t d omega t. Okay, so what will be this equals to? This will be equals to 1 by 2 pi, and this is what this is basically cos pi by 4 minus Vm will be outside, cos pi by 4 minus cos 5 pi by 12, and this is minus, right? So this thing, no, nothing will change. This will be cos 9 pi by 4, or 2 pi plus pi by 4 is basically cos pi by 4 only. 2 pi, like if I add 2 pi with it, it doesn't change anything, right? It doesn't change the angle. So and this will be what? I will just reduce the size. This will be minus cos 5 pi by 12. Okay, so what will be this equals to? This, right? This exactly will be equals to something like this. This will be 2 Vm by 2 pi cos pi by 4 minus cos 5 pi by 12. I will just quickly compute that. So basically this, right, this cos 45 minus cos 75. So what is cos 45? 45 cos minus 75 cos, this 0.448. okay, 0.448. So if I multiply 2 with it, this will be 0.896 Vm, and okay, I have a 2 at the division as well, so I don't need to multiply 2 with it. So 2 will get cancelled. This will be simply 0.448 Vm divided by pi. Okay, so this will be my answer to this question. So obviously you can observe that area has reduced than the previous case. Why has area reduced? Because for basic reasons, right? It has more negative area. Previously it didn't have any negative area. So this is a good question. This is a conceptually good question. If you couldn't understand why this SI is on at that particular moment, just try to quickly go over through it in the like previous course. Like just try to quickly go over through it again, or we can, like, you can understand this in the next lecture where we'll study about the semiconductor converter side. That there also I will explain this in a bit, but if you understood this side, you will be able to easily understand the semiconductor. What is happening? Basically, the inductor is changing everything, right? Inductor is trying to keep a device on so that the current is continuous. That is the most important point here. So next question is this: in a single phase full converter delivering a ripple free load current of 5 amperes. So my load current at IO is equals to 5 amperes is constant. It is a constant load current. Okay. So what are they asking? What is the average value of the thyristor current in amperes? So for a single phase full converter, right, if the load current is ripple free, what happens is that the two thyristors together, the natural pair conducts for a pi cycle, right? For a pi cycle. If you remember, in a cycle of 2 pi, they connect for pi. Okay. And the second half, right, second pi is connected by the other natural pair. So let's say T1 and T2 conduct for pi period from 0 to pi, or from alpha to pi plus alpha, and then T3 and T4 conduct from pi plus alpha to 2 pi plus alpha. So that happens in a normal ripple free load current and in a normal configuration in a continuous conduction mode. So I know, right, for a continuous conduction mode, and when the load current is constant, continuous conduction mode, thyristors, SCRs, conduct for a period of pi. SCRs conduct for a period of pi in a cycle of 2 pi. So in overall cycle of 2 pi, SCRs conduct for pi, right? So what will be the average? So like average will be simple only. I can show you IT average. Like we have computed this earlier as well. I've just shown you the result as well. It is IO into, like, for what period it is conducting, IO into pi. Okay, this is the area and divide by the total time period. Total time period is 2 pi. So this will be simply IO by 2. So this will be 2.5 amperes, right? And now if you want to understand this graphically as well, I can show you graphically as well. So I'll just reduce the size of this. Okay, if I want to show you the conduction of 2 SCR, so I don't know if what is the alpha and all, so I will assume with alpha only there are SCRs. So this is IT1 and IT2. This is omega t, and let's say from alpha T1 T2 are triggered. So T1 T2 start to conduct, and what will be the value of the conduction? Because it is like whatever current thyristors carry, right, that is the same load current, so this will be only 5 amperes. And up until what they will conduct up until pi plus alpha, right? Pi plus alpha. So this will be pi plus alpha, from alpha to pi plus alpha. Then the current will become 0 again. But at pi plus alpha, what will happen? Current needs to be continuous, right? So obviously at pi plus alpha, the thyristor T3 and T4 will conduct. Okay. So the waveforms will be something like this. This will be alpha, and as soon as the T1 and T2 start conduct, they will be 0. Their currents will be 0 only. They will naturally commutated, and as soon as they turn off, right, at pi plus alpha, T3 and T4 will start to conduct. Okay, at pi plus alpha. So like you can simply compute the average, right? They are repeating every 2 pi, so you can compute the average. What is the area? 5 into pi. What is the time period? 2 pi. So I have done that only. That's where the formula came from. This is just a shortcut. Okay, so this will be the average current. This will be the answer to this question. So in the next question, this is a very good question, so do try to solve it by yourself also. Like here, a single phase full converter is given. The VI characteristics of the SCR is shown. So all the SCRs have the same VI characteristics like shown below. If the load current is assumed to be constant, so here, right, they haven't provided us the value of L, and L is very high, then we assume that load current is constant. They have told us in the question itself that we will assume load current to be constant. So the load current is assumed to be constant, then power consumed by the load, power factor of the source, and value of the constant load current. All these things we have to compute. So these, right, actually what should happen is this, right, this should be first actually. Actually the value of the constant load current, power consumed by the load, and power factor of the source. Okay, so this will get cancelled. Yeah, so because like first sequence, if we solve sequentially, right, we'll be able to first find out the value of the load average load current. That is a hint. So this is the SCR characteristics, and alpha also they have given us. The alpha they have given us. Supply they have given. What is the value of supply? Supply is 500 sine 314t. So first of all, we have to understand this, right? We have to understand. So if you haven't studied switches, you have to go through and watch my first chapter. So in the first chapter, right, what we have explained is like how to identify this VI characteristics. Like if you have studied diode as well, you will be able to identify what is this VI characteristics. So here, right, here, what do I mean by this is that my R-on, right? R-on will be what? R-on will be delta V upon delta I. Okay. So in this case, what is my delta V? So what is the delta V I am moving? It is 1 volts. So it is 1 volts. And what is my delta I? Delta I, right? It is also 1 from 0 to 1. So it is also 1. So R-on, right? On resistance of the switch is 1 ohms. What is VD on? So this, right? This from where the slope is non-zero. Okay. This point is known as the VD on. So in this case, right, our VD on is 2 volts. VD on is 2 volts. So here our VD on is 2 volts, and here our R on is delta V upon delta I is 1 ohms. So this is the case. Now what I can say is that I know the switch. Now let's for a second solve this if my SCRs were ideal. Because up until now, what we have been solving? We have been solving for the cases where my SCR is ideal. We haven't thought about the switching losses, this like R on and this V on, right? V on. So this should be not VD because this is not a diode. So this should be only V on. So first, assume, because once you assume ideal switches, then you incorporate the complexities. That is much more easier than at the starting itself you incorporate the complexities. So assume ideal switch. Okay. So if I assume this is ideal switches and at alpha equals 60, I'm triggering T1T, right? Before that, there is constant conduction, and as I don't have any freewheeling diode. Like once you study freewheeling diode, that you understand that voltage can be 0 as well. But as I don't have any freewheeling diode, only natural pairs will conduct. What is a natural pair? Either T1 T2 or T3 T4. So T1 T2 I haven't triggered them, so T1 T2 won't turn on. So T4 and T3 will be turned on, and what is VO equals to when T3 and T4 is turned on? It is minus Vs. So it will be something negative, like it will. We have just analyzed this in the previous lecture. Negative, then at alpha, right? At alpha, it will become positive. As soon as it becomes positive, then it will follow the plus voltage source up until what? Up until pi plus alpha up until pi plus alpha, right? So this will be up until pi plus alpha, then it will be again equals to minus Vs. So after pi, right, my Vs is negative, so negative of that will be simply positive. Okay, so it will be simply like this. Okay, so this is pi plus alpha, right? This is pi plus alpha. So now what I can say, my IO current is constant. My IO current is constant only. It will be some constant value because it has to always conduct. They have told me to assume constant current. So for this case, right, what is my VM average? What is my VO average? So in this case, my VO average is simply, if you remember, VO average is simply 2 Vm by cos alpha, right? Like you can always integrate. It will be 2 Vm by pi into cos alpha. Okay, so this time this will be, right, this cos alpha is 60, so cos 60 is half, so this will be Vm by pi. Okay, this is VO average in the ideal case. Okay, now the important point, what is this value? Actually my Vm is what? Vm is 500, I believe. Yeah, Vm is 500, so Vm by pi will be what? 500 divided by pi is 159.155. So it is 159.155. Okay, so like next, now I will include the non-idealities. Okay, so what are the non-idealities? I have a on, like let's assume for the first case when my SCRs were on. So when my SCRs were on, so these two were on, so this were on with their own on voltages and their resistances, right? On voltages and resistances. So what I will do is, so what is the circuit? Like whatever current IT2 is flowing, that same current IT2 is flowing through this as well and through this load as well. So what I will do, I will transfer this voltage and this resistance to this load to simplify things over here, because everything is in series, because throughout the whole circuit same current is flowing. IO equals to IT2 equals to IS. Okay, so I will write here as everything is in series, IO equals to IT2 equals to IT1 equals to IS. Okay, so if everything is a series, what I can do is I can convert this. What will I convert to? I will make the switches ideal. Okay, but add this voltage drop to the battery voltage E and to the resistance R, right? So R will become, each SCR had 1 ohm, so this will be 10 ohms, and each voltage source had 2 volts, so this will be 80 volts. Okay, so 80 volts and 10 ohms. So these are on, right? These are on. So this is on, this is on. Now this is ideal, right? And for ideal case, what do you know? What VO average I can get? So this is, right, this is what? This is VO dash. But this is VO ideal. Okay, ideal. Because I've assumed that this, like, load is there, whatever, but these switches are ideal. So VO ideal, I know what I can get, right? VO ideal is, I have already computed, 159.155 volts. Now, like, whatever current flows through this, the same current will flow through this, right? Although the voltage drops are different, to the load, but the current will be same, right? Because I've just added them in series. That is the meaning. That is the basic meaning of series, that I can add the things and the current will remain same. Current will change. So can I compute my current here? Yes, right? I can simply compute my current. That what will be my current? IO will be same, right? So IO average would be equals to VO ideal minus E dash. So this, right, this won't be E anymore, this will be E dash, because this is not the actual load anymore. Actual load was 76 volts, but this I added the voltage drop, so it become 80 volts. Here this will not be R anymore, this will be R dash, okay, because it has the switch resistance as well. R actual, in case of actual load, R was 8 ohms, right? So it will be E divided by what? Divided by R, right? R dash. It will be E dash and R dash. So this will be equals to what? This if I compute this real quick, this will be minus 80 divided R dash is 10. So this will be 7.915 amperes. So if I just reduce the size of all this, right? Okay, so this will be 7.915 amperes. Okay, so this average current, whatever I've computed, this is my answer actually, because this will be for both the cases. Everything is in series. IO average will be this only. But what about the power consumed by the load? What is the power consumed by the load? So here, right, I have computed my IO average. So this IO will also be equal to this, because what have they told to assume? They have told me to assume that the current is constant. So this current will also be equals to what? 7.915 amperes. Okay, this one will be 7.915 amperes. So this current is this. Now what can I say? So my power, right, when the load current is constant, is equals to simply VO average into IO average. Okay, this is for the load, and when this formula is only applicable, like this is not the formula, basically I've derived it in front of you multiple times. So this is only for the constant load current. Okay, and this VO average, right, is actually the load voltage. Okay, load voltage. This is not the like overall VO dash. So sorry, this is VO dash, right? VO dash average actually. VO dash average. I'm not talking about VO, right? VO is different. VO is combining the figure of all the switches. So how do I find out VO dash? So like your VO dash, right? Not your VO. So your VO, right, will be equals to VO dash plus all the extra drops. So what I can write is my VO will be equals to VO dash this plus I had what extra drops? I had this 2 volt and 2 volt. So plus 2, like V on into 2 plus IO into R into 2, because I had 2 switches, right? That's why. 2 switches, that's why. So this extra drop was taken into consideration, okay, while computing VO. That's why, because I inserted this here and I have computed my VO. But while computing VO, these were the extra drops that were computed, because in these switches, right, there was extra power loss. Previously these were ideal, hence these were 0 only. So this is what my VO dash is. Now I know V on, I know R, this is R on, right? This is not simple capital R, this is R on. Okay, this R on. So what I can say, I need to find out VO dash, right? I need to find out VO dash. So I know VO. What is VO? VO is simply this value, right? VO is this value, whatever I compute, VO ideal. So it is 159.155 minus V on into 2. What is V on? V on is 2. 2 into 2 is 4 minus 2 times IO into R on. IO is what? IO is 7.915. R on is 1 only, and 2 I have already written at the start. So VO dash will be what? It should be 135 point something. I will just check real quick. Into 2 minus 4. Oh, not minus, plus, then this plus 159.155. So this will be 139.32. Okay, 139.32 volts. Okay. So this is my VO dash average. So this is the average voltage. Now I need to compute the what? I need to compute the power. So how do I compute the power? Power, right? PO will be equal to VO dash average into IO average. So VO dash average will be 139.32 into IO average. It is equals to simply I know already this value. This is 7.915. If I just compute this 7.915, this will be 1102. Okay, this value will be 1102.75. 1102.75 watts. Okay, so this is the answer. Now there is another way to do this as well. So this was the method 1 to find out the power. Okay, method 1. What method 2 can we apply? Okay, method 2 is basically find out the ideal power, PO ideal, and subtract with the P losses, okay, loss in the converter, and by that I will be able to find out my PO actual. Okay, so what is PO ideal? PO ideal, right? As the load is DC, I can directly write this as VO average into IO average, right? And this is the ideal case, minus P loss. What is P loss? So P loss is throughout this thyristor, right? So here, what is the loss? Current is constant. So if current is constant, and what is the loss across resistors? It is IO square into R. There are 2 switches, so it will be 2 into IO square into R. So 2 into IO square. IO is constant, right? Is 7.915 whole square into R. R is what? 1, and plus another loss is the loss across the on drop, right? On V on, right? So V on is DC, so it will be only DC, but here like it is constant current, so DC, RMS, everything is same. So it will be V on into IO, but there are 2 switches, so it will be 2 into V on. V on is what? 2 volts into I is 7.915. Okay, so this will be equals to my PO actual power that the load is receiving, because converter is also taking some power. Okay, so this will be if I want to compute VO average into IO average. So VO average ideal, right? This is the ideal case. VO average ideal is what? This value, right? 159.155. So 159.155 into 7.915 minus bracket 2 into 7.915 whole square, then plus 2 into 7.915. Okay, so switching losses will be this, right? This will come out to be 156 point something. I just computed 156 point something. I just this is not showing it, 156.7 or something. And my PO actual, right? PO actual will come out to be 110.75. You can cross verify by usual as well. It will come out same. So like whatever we have done, right, is same. So you can follow either of these 2 methods, whichever is suitable, whichever you are able to understand better. You can use that method. Okay. So all this we have computed. Now what do we have to compute? We have to compute the power factor, right? So power factor, like you can compute like again with the 2 methods. Method 1 is simply like this, that you compute the load power, right? You compute the load power, PO actual plus P loss will be equals to a supply power. Okay, like that you can see, because your supply has to deliver power to the load as well as loss. I've I computed the power to the load, and the loss is 156. So that overall will be actually this only. Okay, so this value is what? This value is simply, okay, this value is not written here. Okay, this value is 1 2 something, right? I forgot to write this. Oh no, everything is gone now. 7.915 into 159.159 from what 1.155. So it is 1259. So basically your PS, right, it will come out to be 1259. Okay, or what you can do is method 2 is, you can directly write like your PS, right? Supply power will be PO ideal. Why it will be PO ideal? Because whatever power your supply has to provide, right, it will be constant. Okay, some part of it will go to the converter because converter is practical, so it will have some its own loss, and the remaining part will go to load. But whatever power your supply will be pure ideal. That much power, that much is the maximum power that your supply can power if the converter is 100% efficient, and if the converter is ideal. If the converter is non-ideal, then itself, like the converter itself, will take up some power, right, absorb some power. So it will be pure ideal, and which I already computed, which is VO average into IO average. This I have already computed, right? So you don't need to find out loss and all those things for computing the power factor. So this will be 1259.71 watts. Okay, so what will be your power factor? Source power factor, supply power factor, cos phi s will be simply PS upon SS. So it will be 1259.71 upon SS. What is SS? It is VS RMS into IS RMS. So VS RMS is basically VM by root 2. Okay, and IS RMS is basically IO RMS. Why? Because load current is constant and IO square is equals to IA square. So this will be what? Basically, if I divide this, right, VM by root 2. So VM is 500, I believe. Yeah, VM is 500. 500 into 7.915 into, so this will be 0.45. okay, 0.45, right, 0.4522 or like 0, almost 0.45. So this will be the answer to this question. So the power factor and all those things, this will be the answer. So trust me, this is the highest level of what they can ask. So don't worry if you couldn't solve this or couldn't understand this at one go. You can go and repeat it again on loop, and you can go and understand this. What did I explain in this question? This is a very, very good question, and if you couldn't understand, right, please go through it again. And this is the hardest level which they can ask, because this is a lengthy question, right? Because here they are assuming the converter is non-ideal, so we have to assume the what do you say, the basically losses as well, right? We have to understand the losses as well. So next, let's go to this next thing, that is next question, right? This is the next question. Still we have 4 questions. Okay, lot more questions left actually, but next few questions will be simpler than this. Okay, trust me, next few questions will be simple. Last question will be very interesting. Okay, so we'll start with this. So this question, it has given that in a single phase full converter, the average value of the thyristor current is 1.8 amperes. So average value of the thyristor current is 1.8 amperes. Then comment about the continuity of the load current. So we have to comment about the continuity of the load current. So what we can do is, the most easiest thing, when does the analysis become easier? When my load current is actually continuous. So what I will do, I will assume load current is continuous. Okay, so I will assume if I assume load current is continuous, and for that value I get the thyristor average current, and if I see that the thyristor average current, the ideal, like if the load current is continuous, what I am getting, and whatever they have told us, the actual thyristor average current is less than that. So obviously load current is discontinuous because the thyristor current is 0 for some period of time. That may be the reason, right? So here, okay, why did it go? So here, right, alpha they have given me 60. How to get IO average? IO average is what? For a RLE load, right? IO average is basically E minus VO average minus E divided by R. Okay, so in our case, what is VO average? VO average is basically 2 Vm by pi. 2 Vm by pi. VO average is 2 Vm by pi. So it will be minus E. What is E? Okay, sorry, 2 Vm by pi. No, not 2 Vm by 2 Vm cos alpha by pi, right? Cos alpha by pi. You don't need to remember. You can derive, right? You can always derive. So and E is 18 in our case, and R is 10, and alpha is 60. So this is basically half. So this is half. So this will become come out to be 1 by 2, right? This will be Vm by pi only. So if I just do Vm by pi quickly, so 400 divided by pi minus 80 divided by 10. Okay, divided by 10. This will be 4.732. So your IO average will be 4.732 amperes, right? It will be 4.732 amperes. This will be my IO average. What is my IT average? So like for what duration my thyrosis conduct? For the half the duration, right? I've just proven this in the previous question. So IT average, if everything is continuous, right, will be simply IO average divided by 2, which is equals to, if I divide this by 2, this will be 2.366 amperes of current. 2.366 amperes of current, right? Now what have they told me? They have told me I am getting 1.8 amperes of current. So with my assumption, my IT average, this IT average with continuous is actually greater than my IT average actual. So obviously, how can my average value be lowered? If the area is less, right? Area is less. Area over the omega t axis is less. So area, that means if my actual thyroid average thyroid current is lower, that means my area above the omega t is less than what I had initially understood, right? And how it can become less? If there is less conduction, right? Less conduction. If it is 0 for more amount of time than which I supposed that it is 0 for only pi period, but now it is 0 for more duration. If it is 0 for more duration, that means like it will be applicable for the other two high resistors as well. That means what? That means I will just reduce the size of this. This means my load is not in continuous conduction mode. Load is not in continuous conduction mode, right? It is not in continuous conduction mode. It is discontinuous. Okay, so it is discontinuous. So this is the comment. That comment is not continuous. So you assume with the simple thing, and whatever you assume, right? If it what do you say? If it contradicts, if some case contradicts with your assumption, then obviously whatever you assume is wrong. Just like diode, right? If you assume a diode to be on, the current should flow from anode to cathode. It should never flow from cathode to anode. Then whatever you assume is wrong. It is contradicting, right? Same here. Okay, so let's move on to the next question. So in the next question, SCRs with a peak inverse voltage rating of 1000 volts. So we have a SCR with a peak inverse voltage rating of 1000 volts. So okay, fine. and an average on-state current rating of 100 amps. So on-state IT maximum, okay, is 100 amps, and PIV, right? PIV is 1000 volts. Okay. Then what they're telling? Then they're telling that amperes are used in a single phase midpoint converter. So like I have just taken it, okay, just for the sake of it. But if you have studied midpoint converter, right, in the previous quizzes I have taught about midpoint converter. So in the midpoint converter, one important thing is that your peak inverse voltage, right, in peak inverse. So the main points about midpoint converter I will quickly summarize here only. Okay, the working I have explained in my previous quizzes. You have to go and watch that. I'll just quickly summarize what we know about the midpoint converter. Okay, so the peak inverse voltage, right, that we receive in the midpoint converter is 2 Vm actually. Okay, it is 2 Vm. So that is the peak inverse voltage, right? And in our case, the peak inverse voltage they have told us is 1000 volts. So what next they are telling, you will see that in a single phase midpoint converter and a single phase bridge converter. So in a single phase, so this is for the midpoint converter, peak inverse voltage for a single phase midpoint converter, right? I will write this in short. Write this in midpoint converter. And in a bridge converter, what is the peak inverse voltage across each SCR? What is the maximum negative voltage that can come? It is Vm, right? When the other two natural pairs are on, obviously, like the other two SCRs are on, maximum potential in the negative direction, reverse direction, can come Vm. It cannot go over Vm, right? So in case of bridge, right, in case of bridge, peak inverse voltage for bridge is basically equals to Vm. Okay, is basically equals to Vm. So this is the difference. What are they asking? The ratio of power ratings handled by the single phase midpoint converter and a single phase bridge converter, and also they are told using a safety factor of 2 for voltage ratings. So voltage ratings has a safety factor of 2. Current rating will be same because they are like same. They can flow maximum this amount of current, right? So safety factor. So we write safety factor, right? Safety factor is 2 in this case. Fine. The ratio of the power ratings handled by the single phase midpoint converter, ratio of the power ratings handled by single phase midpoint converter and a single phase bridge converter. So what is the maximum power they can handle if the load current is considered to be constant? So what is the maximum power they can handle, right? They can handle. So let me compare with midpoint converter. Midpoint converter and a bridge rectifier, right? Bridge rectifier. So if I see here, right, in case of like what does safety factor means? Safety factor means safety factor is equals to, it is the how much safety am I providing. So my maximum rating by actual voltage, right, that is being used. Okay, so this is my safety factor basically. So if this is my safety factor, so my maximum in this case, right, what will be the maximum peak inverse rating? So here, right, my peak inverse voltage, so like safety factor of 2. So here whatever PIV I have to reduce it by 2. So okay, so here is a peak inverse voltage of 1000 volts. Fine. So what maximum rating can this take, right? The maximum rating this can take is what? Peak inverse is 1000 is Vm, this PIV by 2, because Vm will be this only. Okay, so in this case, right, safety factor is this. So how much maximum voltage I can give here? So what is the maximum voltage I can give? So let's just take an assumption. So each SCR has peak inverse rating of 1000 volts. So if I place here 1000, right? So what is the maximum voltage I can provide? If I provide here 500 volts, like if the VM is 500 volts, if the peak voltage of the sinusoid is 500, then peak inverse voltage across the midpoint converter for a particular SCR, for a single SCR, will be 1000 volts. Okay, 1000 volts. If I provide here VM is equals to 1000, so 1000 sin omega t. If it is 1000 sin omega t, so 2 into 1000 sin omega t will be 2000 volts. So the peak inverse voltage across the SCR will come out to be 2000 volts, which is not allowed, right? Which is not allowed, because maximum I can go is 1000 volts. So here VM maximum can be what? PIV by 2, right? So for midpoint converter, VM max, okay, can be PIV by 2. So PIV is fixed, right? PIV is fixed. So this is not actually PIV of midpoint converter, or okay, yeah, this is PIV of midpoint converter and this, but PIV of SCR is fixed, right? PIV of each SCR, so which is 1000 only. So PIV of SCR, that is fixed. That value is fixed. Okay, so this is what, this is 1000. So PIV of SCR is 1000. So 1000 divided by 2. So maximum value my VM can be is 500 in the midpoint converter, but I have to take a safety factor as well, right? Because I don't want it to like always go at the neck of the maximum value, right? I don't want that device. So what can happen? If shortfall can happen, it can go ever bit, like it can go to 505 volts, it can go to 510 volts. That may damage the device. I don't want that. I want to have a safety factor, right? I want to have a safety factor so that it can never go to that level. I want to have safety. So let's say safety factor is 2. So if safety factor is 2, then what I know. So what will be my actual VM? Actual VM will be VM maximum by safety factor, basically. By safety factor. So here what I can say is like why am I keeping this? So like just as we find this well, then I will explain. So VM max is 500 divided by 2, it is 250. So I will, like, what is the working condition? Working condition is my supply will have a peak amplitude of 250 volts. So if my supply has a peak amplitude of 250 volts, the device at max, the peak inverse voltage across the device at max can go to 2 VM, that is 500 volts. And I have a safety factor of 2, that's why I am not totally utilizing this 1000 volts rating, right? I'm only utilizing up to 500 volts. So even if my, let's say, for some reason, for some fault of the supply, the voltage, peak voltage goes to 550, 600, then I'm safe. Then also I'm safe because the device won't get damaged. All this is done to save the device, right? So if let's say I have to chosen, okay, I will exactly go neck and neck. I will exactly choose this as, I will choose no safety factor. I will exactly choose my VM max, that is 500. So if I choose it 500, what will happen? Peak inverse voltage across a SCR will be 1000 volts. And for some reason, for God's grace, some reason, right? The supply peak voltage goes from 500 to 550. So twice of that, it will be 1100, right? So 100 volts more than the rating of the SCR, I am going above that. So what will happen? The device will get damaged. Okay, that's why there is always a safety factor there. So that's why safety factor is this, and maximum voltage that I can choose, actual voltage safely I can choose according to the given safety factor is 250 volts. But what about the bridge rectifier? What about the bridge rectifier? So for the bridge rectifier, right? So for the bridge rectifier, what I can do is, in this case, my peak inverse voltage, right, VM maximum will be exactly equals to my PIV, because that is equal, right? That is simple equal PIV SCR, because that is how the bridge configuration is made. The maximum voltage that can come across the SCR is VM, which is equals to what? 1000 volts. And I have to again worry about the safety. So my VM actual in this case, right? VM actual will be simply 1000 divided by 2, that is 500 volts. So obviously the current ratings are same, the voltage ratings are different. So basically, right, the power rating, what have they told us is the ratio of the power ratings handled by single phase midpoint and bridge converter. So P midpoint like this power rating capability is defined by the switches SCRs only, divided by P bridge. So what is this? So P midpoint will be what? Basically V midpoint. What is the V actual of midpoint? V actual of midpoint is 250 into I rating, right? I rating is same for both of them because like the current rating is same only. It will be 100 and just hold on. So this will be 500 into 100. So this ratio will come out to be 1 by 2, that is 0.5. So 0.5 will be the answer to this question. Okay, that will be the solution. Let's go to the next question. So in the next question, what have they asked us? A single phase full converter supplies a power to a RLE load with following parameters. Source voltage is 230. Now remember, this is RMS, right? Whenever they doesn't mention anything, whenever they don't mention anything, so this is RMS. At 50 Hz, load resistance is 10, load inductance is 70.7 millihenry, E is 100, Faraday angle alpha is 30 degrees. What are the average values of output current and output voltage when the load current is extinguished at omega equals to 200 degrees, right? Or like at omega is 200 degrees, load current is extinguished. So if load current is extinguished, right? I've thought about this as well. When the load current is extinguished, how my waveform will look. So my waveform will look something like this. My output waveform will look something like this. That is, my VO is this. Okay. Then from 0 to alpha, it will not conduct because device, it has already extinguished. That is my assumption. It has already extinguished. Then from alpha to beta, right? Alpha to beta, it will be equals to simply Vs, right? VO will be equals to Vs. Then from beta to pi plus alpha, there will be no conduction. Then from pi plus alpha to pi plus beta, again it will be equals to minus of Vs. Okay, so that will be the case. So what are they asking? They are asking us the average values of voltage and current. Okay, so if I find out average value of voltage, I will be able to simply compute the average value of current as well, because I know R, I know E. Okay, so what I can do is I can simply find out the VO average. What will be VO average? So VO average, like if you remember the formula, well, but let's say I don't remember the form, right? How will I derive? So this will be simply 1 by pi, like from alpha to beta, right? From alpha to beta, I will totally follow the input. So from alpha to beta, this will be equals to my Vs, and from Vs d omega t, from beta to pi plus alpha, it will be E. Beta to pi plus alpha, it will be simply E. Okay, d omega t. So this is throughout the cycle from alpha to pi plus alpha. This is what is happening, right? So 1 by pi, what is Vm? Vm is 230 root 2, right? 230 root 2, which is 325. This will be what? This will be cos of alpha minus cos of beta. What is alpha? Alpha is simply 30 and beta is simply 200 degrees, right? So 30 minus cos of 200 degrees. Cos of 200 degrees plus E is what? E is 100 volts. E is 100 volts into pi plus alpha. Like this will be in radians, right? So alpha is 30. So pi by 6, right? Pi by 6 is in radians. So pi plus pi by 6 is 7 pi by 6 minus this beta is what? Beta is 200. So if beta is 200, so this I can write it like this: 200 divided by 180 into pi. Okay, this will be the value. So I will just compute this and then I will say the answer. So VO average will be simply, let me just change one thing. Yeah, VO average is simply, this is cos 30, right? Cos 30 will be root 3 by 2 minus 200 and times 325. So this will be 586.85. So this will be almost equals to 1 by pi is here, 587 plus 100, and this was 7 into pi divided by 6 minus 200 divided by, okay, just hold on, 7 by 6 minus 200 divided by 180 into pi into 100. So this will be 17.45 actually. This will be, it's not that much. And what will be this equals to v, what will be VO average? So this I have derived, right? Why will the waveform be look like this? You have to watch the previous lecture. So this will be plus 587 divided by pi. So this will be 192.4 volts. Okay, this will be 192.4 volts. This will be my VO average. Now what will be my IO average? IO average is again simple, right? IO average is again simple. Average is VO average minus E divided by R. So it is basically equals to, what is VO average? 182 minus 100 divided by 10, right? R is 10. So R is 10. So it is 9.24 amperes. Okay, so this will be my answer to this question. This is like pretty simple, pretty standard question. I told you, right? No need to remember formula. Did I remember the formula? I directly derive, right? I directly derive here. Did I remember anything? No, right? So that is what mental, that is the type of mentality that I want to install in you, right? You don't need to remember this formula, like this formula, right? You don't need to remember, because most of the educators, they will tell you remember this. Okay, I will tell you not to remember this, because you have so many things, and in power electronics there are so many things to remember. What things you need to remember? How the circuit works, that you definitely remember, because that will be very, very helpful. Okay, like if you understand, if you have the basic understanding of this full wave rectifier with RLE load for discontinuous conduction and continuous conduction, that is the most important part. That's why I focus on the derivation part. That's why I focus more on the explanation part than simple the formula derivation, right? So like I have skipped the formula derivation. I've just directly written the results. Like I've just written the first step and the last step. Okay, you can derive. That is just mathematical thing. You can derive, right? You know mathematics, you know integration, but you don't know this. Don't know this concept. Okay, how to solve this type of question without remembering the formula. That's the most important thing that I want to take away from this question, right? So this is the next question. So in the next question we have a single phase full converter again. Like why are this called full converter? Because all of them I can control, right? Full control. But in the next lecture we'll understand about semi converter. There I can't control all of the switches. I can control a part of them. Okay, I will like that we'll understand in the next lecture. The average value of the output current is 10 amperes. Like they have told us, the average value of the output current is 10 amperes. Then the power delivered by the source. What is the power delivered by the source? So here okay, so average current is 10 amperes, right? So basically the power delivered by the source will be simply what? The load is battery and inductor. So what have they asked? They have asked the power delivered by the source. So converter is ideal, right? Converter is ideal. So like they haven't mentioned anything. So I will assume ideal converter. I will assume an ideal converter. So basically my PO, right? Like power delivered by the source will be the power consumed by the battery, okay, plus the power consumed by the inductor. And what do I know? In a cycle the power consumed by the inductor is simply equals to 0 watts. Okay, so overall my power supplied by the source will be power consumed by the battery, and battery is a DC load. So battery is a DC load. So for a DC load, what is the power formula for a DC load? Like this I have derived previously, so I will write this directly here. For a DC load, the power formula is V average into I average. And what is V average for the battery? It is E, right? It is always constant E. What is I average? It is IO average. So IO average is this. So have they told me the average current? Yes, right? They have told me the IO average. So IO average will be this, and E right, E is 80. So 80 into 10 is equals to 800 watts. So I cannot comment about the continuity, discontinuity. All those things I can obviously comment if I'm able to find the average current or the average output voltage, right? So they haven't told me any firing angle, all those things. So I am not able to comment about the continuity, but what I am able to comment is this thing, right? This thing, like this power consumed will be definitely 800 watts. So these type of trick questions can come. So you see, right, the question was very small. Duration it took me to solve the question was very small, but the concepts are important. Concepts are very important. That are you able to understand? Are you able to go sequentially? Are you able to think? So you will be only able to think when you solve the questions by yourself. Okay. So this question is the next question. This is the most like interesting question. So what you can do, you can again pause the video and again. So if you couldn't, you can again solve the video if you have gained some knowledge, gained some perspective, right? So obviously for you to solve this question, you have to study the first chapter. So in a single phase full converter supplies power to a pure resistive load. So load is pure resistive. Vs is 400. Again, if they haven't mentioned anything, so this will be simply RMS. This will be simply RMS, and then find the average voltage for the following cases. So you have to find the average output voltage. Okay. So here frequency and TRR. What is TRR? Frequency, F is the frequency of the supply and TRR is the reverse recovery time of each diode. So if you haven't studied that concept of reverse recovery, you have to go back and go watch the reverse recovery, right? So basically here, right, my alpha is 0 because these are diodes. My alpha is 0. So let's say if everything was ideal, okay, alpha is 0. If there was no reverse recovery time, okay, if you don't know what reverse recovery is, you have to go back and watch my first chapter, right? There I have explained. If there was no reverse recovery time, if this was ideal converter, what would have happened? Simply from 0 to pi, this would have been plus Vs. From pi to 2 pi, this will be minus Vs, right? So pi 0 to pi. If I had the diodes were ideal diodes. But now what is happening is that, like this diode, right, what is happening? To turn off, it is taking some time. So here reverse recovery, okay, this was already on, and to turn off this was taking some time. So here what will happen is that, let's say I'm at this point. So here what is happening in this region, right? Exactly at this, a transition is happening. What transition? My D1, D2 is going to off and my D3, D4 is on. Okay, turning on at this instant, at this particular instant. But here what is happening is that as soon as my D1, D2 is turning off, right, it is not actually turning off in a practical case. Why? Because I have some finite reverse recovery time, right? So to turn off, right, the charge carriers are still present inside the diode and it is not turning off. So as it is not turning off, still it is on. So in that case, if I draw the circuit, right, between just at omega t equals to pi, okay, just add omega t equals to pi. What is happening is that, okay, I didn't name these diodes. This is D1 and D2, like generally I name them, so I will name them. So let's say this is D1 and this is D2, just same naming convention as the thyristor. So what did I name the thyristor? This was D3, right? Yeah, okay, so this will be D3 and D4. Okay, so now, so this D1 and D2 just at omega t equals to pi were supposed to turn off, but they didn't turn off. Why they didn't turn off? Because what will happen is, basically there is a reverse recovery time. So I have to remove the charge carriers. They are still present in the inside of the diode. So diode will still conduct. So they will not turn off. And what is the another condition? That my D4 and D3, right, they will turn on because I am from pi to 2 pi. So in the pi to 2 pi region, they will turn on. So what is happening? My supply is getting short circuited. which is very very dangerous. We have a few measures, we take few protection measures, but like that is out of scope, so we will not understand that, we'll not like study about that, so that is out of the scope. But supply is getting short circuited. But here, right, what is happening to VO? So VO is actually going to be 0. So if you apply simple KVL, right, VO will be 0. You apply from here, so all 4 diodes are on. So that is actually what is happening. So in practical case, right, in practical case, I have a theta RR, and that is the delay by which this diode is finally getting off. So as soon as this diode is off, sorry, not this diode and this diode is finally off at theta RR, that is equals to omega into T RR. Then what is happening is that finally my output voltage is equals to minus of Vs. So my voltage, right? So if I just hold on a second, let me check if everything is recording or not. Yeah, everything is recording, fine. So VO actual, okay, so this will be simply like it will be 0 up until this theta RR. Like theta RR is just a notation. Theta RR is actually what I will just explain, and then again suddenly the diodes turn off, so the all the voltage comes across the load again. So this will be equals to Vs, and it will follow the input just like the previous case. But at pi again, the D1 and D2 tries to turn off, but it can't turn off, so it is still on. So it will be on till theta RR. Okay, then again it will be minus Vs, and then it will be 2 pi. So this side, this will be pi, this will be 2 pi, this will be pi plus theta RR. Okay, so this will be 2 pi plus theta RR. Okay, so what is the theta RR? Theta RR is actually omega into TRR, because after TRR time, right, the diodes are finally able to turn off because there is a reverse recovery time, that is a omega into TRR. So the output voltage, right, average value of output voltage will change at different TRR. So there are 3 different cases, so we'll analyze the 3 different cases. So here for the first case 1, okay, case A, my F is 50 Hertz, and what is my TRR? TRR is 100 micro, right, 100 microseconds. So what will be the output voltage expression, average output voltage expression, if I want to compute, right? Theta RR is some variable, depends upon TRR and omega, right? Depends upon TRR and omega. Omega is also changing and TRR is also changing. So what is my VO average? VO average, right, will be simply 1 by pi, because it is again repeating after every pi only. But this will be like there is, like it's almost like there is a triggering angle. So theta RR into from pi, okay, equals to Vm sin omega t. So like this is very dangerous. Although SCRs were back then were blocking the voltage, but this time diodes won't block the voltage. So that is very dangerous. We have few precautions in place for all this, so that we will understand in protection. That is for other day. So this is like, this will value will be what? This will be simply Vm by pi one plus cos theta. Okay, so this will be the value. This will be the value basically. So this will be the average voltage. So I will, like for each of the cases, I will compute theta RR. What will be theta RR1? Theta RR1. This is my F1 and theta TRR1. Theta RR1 will be, this is 2 pi F1, right? 2 pi F1 into TRR1. Okay, am I right? 2 pi. Just hold on. Omega t, yeah, omega TRR, yeah, fine. Like theta RR is actually omega 1 into TRR1. So this is the value. This, so 2 pi F, like 2 pi is 100 pi into 100 microsecond, right? So what is happening? This is 10 raised to the power 4, 10 raised to the power minus 6, this is 10 raised to the power minus 2. So 10 raised to the power minus 2 into 3. So 10 raised to the power minus 2 into pi. So this will be almost 3.14, 0.0314. Okay, this will be the value, but I want to compute this in the angle, right? This is in the radians. I want to compute this in the angle. So pi divided by 100 into 180 divided by pi. So this will be 1.8 degrees. So this will be 1.8 degrees. So theta r is this. What is my VO average? VO average is Vm upon pi. Vm is basically Vm is 400 volts. And this is not Vm, right? This is RMS. So this will be Vm will be 400 root 2, right? This will be 400 root 2 divided by 1 plus cos 1.8 degrees. Okay. So this will be almost 360.03 volts. Okay, this will be almost 360.03 volts. Now what about the part B, right? But like second case. So second case, my F2 is simply 50 hertz only, I think. 3 kilohertz, and TRR is same only, 100 microseconds. So this has gone to 3 kilohertz and TRR2 is gone to 100 microseconds. So basically it is like 6 times that, right? Like how many times is that? Almost 60 times, I think. Almost 60. So if I multiply 1.8 or 60 or like 10 times. What am I thinking? 3, 10, 1.8. Just 6 times this only. 60 times only, I think. So if I do 1.8 into 60. So yeah, my theta, like 50 into 60 is 3000. So my theta r, right? So you can compute theta r2, it will be almost equals to 108 degrees. So what will be your VO average? Average to, what will be your VO average to? This is VO average 1. What will be VO average to? VO average 2 will be equals to Vm by pi. Vm by pi again 400 root 2 by pi into 1 plus cos theta r. So cos 108 degrees. So cos plus 1 into 400 into root 2 divided by pi. So this is equals to 1 to 4.42. So this is very bad, right? Very bad. And this is very dangerous because my supply is short circuited for a much longer amount of time. Okay, very bad. Why is this the case? Because my TRR is same even if I increase my supply frequency. So I will put the conclusion at the end after computing the third case. So this is not ABC actually. This is 1, 2, 3, 8. Okay, sorry for that. So in the third case, what will be your theta? So in the third case, right, your F3 is actually 3 kilohertz, but your TRR has also increased now. F3 decreased now. So your F3 in the third case is basically 3 kilohertz only, but your TRR has reduced by 10 times. So F3 is 3 kilohertz and your TRR3 is reduced by 10 times, 10 microseconds. So obviously what I can say? I can say that my theta RR 3 is 10 divided by the previous case, that is 10.8 degrees. So obviously my VO will improve a lot. Okay, it will be simply, I will just directly compute now, 400 into root 2 divided by pi into 1 plus, what is theta RR? 10.8 cos. So this, okay, what happened? This became very pi and divide by pi, I think. Yeah, this will be 356.938 volts. Okay, so this is almost near the first case that I got. So this is very good. Okay, good. What change here? What change Basically I reduce my TRR. As my frequency increased, my TRR I reduced. What do I mean by reducing a TRR? Basically I am using a switch of higher switching frequency, because as my frequency increases, that is FSW increases, my TRR will reduce. Why? Because why is that the case? Because my F switching, right, is inversely proportional to the time, basically proportional to the time, and obviously if I increase this, right, this has to reduce, right? That's why. So here, that is the conclusion basically for like basic conclusion of switches. If the frequency of the supply is very high, then we must use switching devices rated with high switching frequency. Else I will say here, else there will be high switching losses. Like basically, right, I'm not getting my desired average voltage. Now where did the average voltage gone? Like where did it wipe out? It wiped out to the switch, right? So there is high switching losses, right? Like high switching losses will occur in the switches. Okay, so if I don't use, like if my supply is of high frequency and the switches that I'm using are rated for low frequency, that will be very bad for the working of the device. There will be huge losses. So if the supply frequency is also high, we have to use switches of high frequency. So basically that's it for this lecture. We did a lot of problems, and please go through them again, because this is a very good lecture, and we did some very good problems that haven't like come in gate examination yet, but that can come in. These are future questions that can come in gate examination. So I have taken the practical switches in the rectifier setup. Generally many like educators, they don't teach all this, right? So yeah, thank you for watching, and I will see you in the next lecture.